This video will apply the concept of horizontal asymptotes to different types of functions. The definition you can see gives us two limits to consider. However, firstly I want to acknowledge an assumption that is usually made whereby students interpret the horizontal asymptote to be found using this second definition. This misconception is made because the vertical asymptote is found by analysing what x cannot equal or what value is excluded from the domain, and therefore the asymptote is something the graph does not pass through. We will see why this is incorrect for the horizontal asymptote. As it is incorrect, I will get rid of it before it settles in anyone's brain. Note we need to consider both the case where x tends to infinity and when x tends to negative infinity, as it is possible to get two different results. We can, therefore, conclude that a function has at most two horizontal asymptotes. I will start by looking at rational functions. We can start out by thinking intuitively before formalising a method to find the limit. If we think about this fraction of 2x over 1 minus x as x gets very large, in the millions for example, we can see that the 1 becomes insignificant and we are getting closer and closer to dividing 2 times the quantity by negative 1 lots of that quantity, which equals to negative 2. To formalise this, we can think about manipulating this fraction by dividing the numerator and denominator by x. Here we can see that 1 over x will get increasingly close to 0 as x tends to infinity, giving us the same result. Therefore, y equals minus 2 is the horizontal asymptote. We should also consider the limit of the function as x tends to negative infinity. Applying the same manipulation leads us again to conclude that 1 over x will tend to 0 as x tends to negative infinity. Although this gives the same result, there is a difference. As x approaches negative infinity, the denominator will approach negative 1 from the left-hand side, so it will always be slightly less than negative 1, which means the fraction will approach negative 2 from the right-hand side. It will always be slightly more than negative 2. Whereas, when x approaches infinity, it approaches negative 2 from the other side. I will draw in the vertical asymptote of x equals 1, and then we can sketch the graph to see that although there is one horizontal asymptote, approaching that limit is different at either end of the function. Next, let's increase the lead power of the numerator and denominator of the rational function. This will lead us to see why manipulating the fraction is important, as we will now see that terms that originally involved a power of x will become insignificant, and it is not just the constant terms we should ignore. Dividing the numerator and denominator by x squared shows that the lead coefficients are the only significant values when evaluating the limit. This gives us an asymptote of y equals a half. Again, intuitively this works if we consider the vast difference between, say, 1 million squared compared to 1 million. So it is indeed only the highest powers which dictate the limit of a rational function. Some teachers may just say, divide the lead coefficients to find the limit, and this is exactly why. To be thorough, let's consider the limit as x tends to negative infinity, but we can clearly see we will get the same result as terms will still tend to 0 apart from the coefficients of x squared in the numerator and denominator. We can now consider when the numerator is 0 in order to find the vertical asymptotes. Note here that the number of vertical asymptotes is not restricted. We could form a rational function with a cubic as a denominator with 3 real roots in order to get 3 vertical asymptotes. I have sketched in the function to show something important here, that it is possible for the function to equal the horizontal asymptote, which is a clear difference to the vertical asymptote. This is why we had to reject the second definition. We can see that there is a value when x is greater than 3 over 2, when the function equals a half. We can confirm this algebraically by setting the function equal to a half and then solving. Therefore, when x equals 3, the function drops below the asymptote before it will rise again and tend towards it as x tends to infinity, approaching the limit from underneath, whereas as x tends to negative infinity, it approaches the limit from above. These two examples lull us into this belief that we can just consider one limit, as it appears when x tends to infinity and when x tends to negative infinity, we get a similar answer. So let's consider another type of function, e to the x. The function e to the x itself has a horizontal asymptote of y equals to 0, which is found by considering the function as x tends to negative infinity. When x tends to infinity, there is no asymptote. But let us consider this function h of x instead. As x tends to infinity, we can see, by a similar manipulation, that the function will tend to 3. However, let us consider as x tends to negative infinity. It is now the constant terms which become significant, which we have not seen before, as 3e to the x and e to the x will approach 0 as x approaches negative infinity. This leaves us with 5/1, giving us a limit of 5. To round things off, does this function have any vertical asymptotes? Can e to the x plus 1 equal to 0? Without rearranging to solve, we should know this is not possible, as e to the x and 1 are both positive. So e to the x plus 1 must be greater than 0. We should be more specific actually, as we know it is actually greater than 1. The aim of this video is for you to understand the difference between horizontal and vertical asymptotes, as well as giving you a method to find vertical asymptotes. I hope it has been helpful.